By the time the Chicxulub meteor put an end to the age of the dinosaurs, life had already been flourishing on Earth for more than 3.5 billion years. Indeed, in the first 10% of the life of our parent star, the Sun, life emerged in abundance on this planet. Why did this happen so fast? And why has it not emerged elsewhere? The answer to the first question involves the atomic raw materials that are available and the molecule-level conditions which obtained on the early Earth. The answer to the second question, why hasn't life emerged elsewhere, is maybe it has. The precursor molecules of life are abundant in interstellar space. As we shall see in more detail in upcoming lectures, new stars and the planets that frequently accompany them are born in clouds of gas and dust in interstellar space. In most of the volume of interstellar space, there is only about one atom, and you remember how small an atom is, for every cube about 10 centimeters on a side, about the size of this Kleenex box. There's one atom in there, and there's one atom over there, and there's one atom over there. That's really empty space, because in this box right now, just full of air, there are about 10 to the 21 atoms in the air in this room. So interstellar space is really empty. Furthermore, in most of that volume, the temperatures are extremely high, about 1 million degrees, heated by the explosions of stars over the course of the life of the galaxy. So the individual atoms that are there, mostly hydrogen of course, are running around with extreme rapidity. When they collide with each other, they knock their electrons out of each other's orbit, and the material is, by and large, that fourth state of matter, which we don't see often on Earth, called a plasma. Now, there are regions of space that manage to cool off. And where the gas gets cooler, it starts to collect. Denser regions arise until the atoms reach densities of thousands of atoms per cubic centimeter. A sugar cube is about the size of a cubic centimeter, and rather than one atom in a space this large throughout most of the hot regions of space, there are clouds where there are 1,000 atoms inside this sugar cube. Now again, this sugar cube contains more than 1 trillion atoms at the moment, but relative to earthbound things, space is still empty. But this is a dense region of space. As the matter gets denser, that means there's more mass. When there's more mass, there's more gravitational attraction. And so, the little clump of matter over here that's managed to cool itself down, have its electrons join up with its atoms, become a gas rather than a plasma, the atoms exert a gravitational attraction from material over here, which falls slowly towards it, and material over here, which falls slowly towards it. Well, that of course just creates a larger mass here, which has an even greater gravitational force, which extends farther out into space, so that mass here and here and here all start falling towards this region as well. Gradually, over the time scale of millions of years, these cold regions can accumulate the mass of thousands to millions of stars, huge amounts of matter, concentrated in a cloud that's only about 10 degrees above absolute zero. In other words, the atoms are moving around very, very slowly. So many atoms are there, and they're moving so slowly, that they tend to bind together to make molecules. So we call these structures in space molecular clouds. And of course, since hydrogen is the dominant element in the universe and forms molecules easily by linking two of them together, the vast majority of these clouds are made of 2 hydrogen atoms stuck together, H2. These clouds are also filled with tiny particles of dust, far too small to see with the naked eye, which range from collections of tens of thousands of atoms that are all stuck together in a quasi-solid to really little grains that you could almost see made of carbon and iron and other such elements. On the surfaces of these dust grains is a place for atoms to meet up. The dust grains, because they get bombarded occasionally by the same cosmic rays that produce radioactive isotopes in the atmosphere of the Earth, spew off electrons, and so the grains become positively charged. Atoms that stick to them, then, can move around on the surface and eventually can find each other to link up. In interstellar space, even though the cloud is dense, there's still huge space between the atoms. In the air in this room, the atoms are about this far apart if each fist represents one atom. In these molecular clouds, the two fists would be blocks apart. And so the odds of them coming together, and coming together slowly enough that they just gently merge and share their electrons to make a molecular bond, is small. On the surface of these dust grains, however, as they vibrate around on the surface, they can meet up with each other and link together because, first of all, they're moving more slowly, and secondly, they have a solid surface on which to rest. We detect these molecules formed on these dust grains and subsequently ejected back into the gas through the microwave radiation they emit. In addition to the jumping between electron levels of an atom, which emits mostly visible light that our eyes can see, these molecules with 1, with 2, 3, 4, 5, 6, up to 15 atoms together manage to undergo two other kinds of excitation. One is they vibrate. You can imagine them as two little balls connected with a spring, and given a little nudge from a passing atom, they'll vibrate like this. Now, just as the electrons orbiting the nucleus of the atom can only exist in specific orbits and therefore only have specific energies, the transitions between which give rise to light, these little vibrating springs can only vibrate at certain frequencies, this fast, or twice as fast, or 4 times as fast, and so also give off only certain frequencies of light, giving a unique signature to that molecule. Finally, there's a third mode of even lower energy excitation in which if a molecule gets bumped into, it can sort of tumble, rotate around. And again, it can't rotate at any speed. It can rotate this fast, or it can rotate twice that fast, or it can rotate 4 times that fast, but not at speeds in between. Again, giving a unique signature to each molecule. These types of excitations, vibrational excitations and rotational excitations of molecules, give off radiation between the infrared octaves of the spectrum into the radio octaves of the spectrum. In other words, long wavelength light, because they are much lower energy than the little electrons which are zipping around the nucleus of the atom. When the electrons change levels, they give off high frequency light, eyes can see. When these vibrational modes or rotational modes give off energy, it's much longer wavelength light that only radio telescopes or infrared telescopes can pick up. Nonetheless, the important point is that each different kind of molecule, water, carbon dioxide, or whatever, has a unique set of modes in which it can vibrate and rotate, and therefore gives off a unique set of specific frequencies which, when measured with a telescope, can identify that molecule. Over 140 different molecules have already been discovered, most of which contain the most common elements, unsurprisingly, hydrogen, carbon, nitrogen, and oxygen, but also including things like silicon and sulfur. After H2, the most common molecule is carbon monoxide, a carbon and an oxygen atom joined together. And its radiation dominates these interstellar molecular clouds. But water and ammonia, 2 common elements on Earth, are also present. Many of the molecules are carbon-containing organic molecules present in all life on Earth, such as ethyl alcohol, formaldehyde, and acetic acid. These exist in enormous quantities in these molecular clouds in interstellar space. The most complex molecule discovered to date has 13 atoms joined together. But there are many signals in the radio part of the spectrum which signal the presence of molecules but remain unidentified because we haven't synthesized those molecules in the lab and made them vibrate and rotate to reveal their secret wavelengths. It's clear, however, that the raw materials for life are present in all newly formed solar systems because all such solar systems emerge from these molecular riven clouds. The meteorites in our solar system, the rocks left over from its formation which fall to Earth, show that even more complex organic molecules came together in the early solar nebula as the planets and the sun were forming. Analysis of the interiors of meteorites which have fallen to Earth show that they contain purines and pyrimidines. Purines are 5 carbon atoms, 4 hydrogen atoms, and 4 nitrogen atoms joined together, and are 2 of the 4 chemical bases of DNA, adenine and guanine, the genetic code of life. And pyrimidines are the other code. There are 4 carbons, 4 hydrogens, and 2 nitrogens, and they form cytosine and thymine, the other 2 letter codes of DNA, plus uracil, the code in RNA for translating the DNA instructions out to the rest of the cell. Meteorites also contain a number of the 20 amino acids, which are the basic building blocks for all proteins, and therefore the basic molecules of life. Now, a remarkable fact is that these molecules in meteorites and in Earth-based life are left-handed. What do I mean by left-handed? Many complex organic molecules come in 2 varieties, which are chemically identical. That is, they contain exactly the same number of each kind of atom. The sole difference between them is the 3-dimensional arrangements of these atoms. One is the mirror image of the other. There's nothing you can do to fit a right-handed glove onto your left hand. You can turn it around, you can turn it upside down, but there's no way you can make it match perfectly. Likewise, when you hold up your hand to the mirror, you get the reverse image. A mirror image molecule is one that's the same. You hold it up to a mirror, you get the reverse image. There's no way you can rotate the molecule so it looks the same. In fact, the same atoms are there, but they form a mirror image of each other. It turns out that these molecules are called right and left-handed because of the way they treat light. Light, as we learned in one of the early lectures, is a wave. It's a wave of electric and magnetic fields. And if I were to try to reproduce that with my hand, it would look something like this. The electric field grows and falls. And in response, the magnetic field grows and falls in a perpendicular direction. So a propagating light wave looks something like this. My students have made a little dance out of that routine. If we follow just the electric component of the field, the wave goes up and down like the wave of water. But there's no reason that a molecule emitting such light needs to go up and down in this plane. It could go up and down in this plane. It could go up and down in this plane. There are an infinite number of rotations of that plane of oscillation for the electric wave. Polarized light means light which has restricted the modes in which the wave oscillates. So light that is purely polarized means that all the waves are going up and down in this direction, or alternatively, all the waves are going back and forth in this direction in terms of their electric field motion. Polarized sunglasses work by providing a little picket fence in the plastic of the glasses, such that the light, say reflecting off the hood of your car, that's polarized in this direction comes in and sort of buries itself in the hood of the car, and so doesn't shine off and glare in your eyes. The light that's coming in polarized in this direction does bounce off the hood of the car very easily and would come to your eyes and make a blinding glare unless you had a little picket fence in which the light could clatter against and not get through. Polarized sunglasses then pick out a particular orientation of the oscillation of the waves of light. Right and left-handed molecules also pick out particular planes of polarization in just the same way. And if you have a little vial of right-handed molecules in which the polarized light is going this way, it will actually rotate that plane of oscillation to the right as it passes through, whereas left-handed molecules cause it to rotate to the left. That's the name right-handed and left-handed molecules is because they rotate polarized light in opposite directions. Now, all of the amino acids, all 20 of them, which have a handedness, some of them don't have a handedness, but many of them do, that are found in all forms of life on Earth are left-handed. All of them, left-handed. You would think naively, if you just shake up some molecules in a test tube before life exists, you get an equal number of right-handed and left-handed ones. But life on Earth today consists of only left-handed amino acids. Remarkably, when we look in the meteorites for the amino acids that exist there, we also find a preponderance of left-handed molecules. These are the most ancient objects in the solar system, and somehow they have already had imprinted on them the notion that molecules are preferentially left-handed. It's possible to speculate on the origin of this asymmetry. I find this a fascinating and delightful speculation, but I can't argue that it's unquestionably true. As we shall see, there is good atomic evidence that a massive star exploded in our vicinity just as the solar system was being born. The radioactive isotope aluminum-26, which when it decays on a relatively short timescale turns into magnesium-26, an isotope we find a lot of in the solar system, is prevalent. The only way you can produce this short-lived radioactive isotope is in the explosion of a massive star. Now, such explosions often leave behind bizarre objects called neutron stars, where the mass of an entire sun has been compressed into something the size of Manhattan, 10 kilometers across, the size of the meteor that wiped out the dinosaurs. That means the atoms, and actually the atoms are crushed out of existence, so the protons and neutrons are packed together to such a density that the entire object has the density of the nucleus of an atom, 1 billion tons per teaspoonful of matter. This sugar cube would weigh 1 billion tons. These bizarre objects have a number of properties which we'll explore in a later lecture. But one of them is that they spin very rapidly, and because of intense magnetic fields, send out along their north and south magnetic poles spirals of circular waves of light, on the North Pole rotating in one direction and on the South Pole rotating in the opposite direction. Now, when molecules that have a handedness absorb light that's going in the same direction as they are, they're excited. When they accept light going in the opposite direction, they tend to be destroyed. Right-handed molecules are destroyed by left-handed circular polarization. And that can produce an excess of lefties, say 10%. My Columbia chemistry colleagues have actually shown how a small initial asymmetry could be amplified to left-handed dominance under conditions that are expected to prevail on the early Earth. In this scenario, a star explodes and leaves a neutron star behind. The light from one pole of that star irradiates the cloud that will become the solar system and produces a preference for left-handed molecules, perhaps an excess of 5 or 10%. My colleague Ron Breslow and his student Mindy Levine have exposed 5% excess left-handed amino acids to the hot, dryish conditions with a little bit of water that are probably appropriate to the early Earth. And they have found that the left-handed molecules and the right-handed molecules in the solution tend to bind together and crystallize and fall out of the solution, leaving only the excess, the 5% excess of left-handed molecules free in the solution to wander around and connect to other molecules, making them more complex, things perhaps like proteins. This is a fascinating notion that the explosion of a star and the irradiation of our nascent cloud with circularly polarized radiation could have produced a small preference for left-handed molecules, and then the conditions of the early Earth could have amplified that preference to the point that every amino acid on Earth today is left-handed. The fact that the left-handed preference is also seen in the meteorites gives some credence to this story. The young Earth had conditions that were reasonably conducive to the formation of life. What do I mean by life? We have to begin with a very simple definition of life, stripped to its bare bones. I define life as a self-reproducing chemical system capable of Darwinian evolution. Now, that may not sound much like your mother-in-law, or it may sound like your mother-in-law, but it's a good bare bones description of what life is like. Clearly, we would all agree that life must be self-reproducing. That's an essential element of life, that it reproduces itself. Rocks don't do that, bacteria and humans do. Secondly, my suggestion is that life is a chemical system. Now, science fiction writers have imagined non-chemical based systems to be alive. For example, the famous astrophysicist Fred Hoyle, who doubled as a science fiction writer, wrote a wonderful book called The Black Cloud in the 1950s, which, as in most good science fiction, was more about the humans than the creatures from afar. But the thing that was alive in that story was a large dark cloud, perhaps one of these interstellar clouds suffused with dust, whose intelligence was conferred by the threaded magnetic field through the cloud. I'm not saying it's inconceivable that there could be a kind of life, even intelligent life, that's not based on chemical molecules, but excluding that from our definition is a conservative hypothesis. It's important to remember that chemistry is identical everywhere in the universe. The atoms of carbon that exist in my thumbnail are identical to the atoms of carbon in the most distant quasar I can see across the universe. Furthermore, the rules under which those atoms of carbon join together to make chains, or join with oxygen or nitrogen or other kinds of atoms to make complex molecules, are identical across the universe. So when I say life is based on chemistry, I don't have some chauvinistic notion of our chemistry or my chemistry. It's the chemistry of the universe. And it will operate on the early Earth the same way it operates in the most distant galaxy we can see. So, self-reproducing and chemical, the third component of life is that it's capable of undergoing evolution. Means it must transmit instructions from one generation to the next in a mechanism that allows mistakes, errors in transmission, which can therefore be subject to natural selection and therefore change, speciation. This definition requires that molecules store information. If they have to pass it on to the next generation, they surely have to store information in some way. And therefore, the molecules must be reasonably complex. H2, two hydrogen atoms joined together, or even H2O for that matter, an oxygen joined to two hydrogens, is not very complex. It can't store a very large amount of information, and putting a lot of them next to each other doesn't help very much. The actual molecules that store information in living creatures on Earth, of course, is DNA, which is a rather complex molecule consisting of thousands of atoms joined in very specific patterns, which can then transmit information to the next generation. This assumption of complex molecules requires that we need a moderate temperature. Temperature, you will recall, is just a measure of the speed with which atoms or molecules move. If it's too cold, the atoms move so slowly that they rarely meet up with each other and join together. If it's too hot, on the other hand, as soon as a molecule forms, it'll be smacked by another molecule, which is then instantly breaks it apart. And so complex molecules will not evolve. Complex molecules are also most easily formed in the liquid state. Recall in a solid that atoms and molecules are locked in place. They can't move, and if they can't move, they can't migrate to join up with other friends and build something complex. In a gas, the molecules are free to run around, but they encounter each other rarely, and when they do, they tend to bounce off each other like billiard balls. So liquid is a reasonable compromise between these two states. In a liquid, the atoms are touching, or the molecules are touching, so they're close to each other, they find lots of friends, but they're free to slide over each other, and therefore to migrate through the liquid. Water, liquid water, is made of the two most abundant chemically active atoms. The most abundant element in the universe, hydrogen. The second is helium, but that can't make molecules with anything, so cross that out. And the third most abundant atom is oxygen. So the two most abundant chemically active ones join together with one oxygen and two hydrogen attached. It's not true that water is absolutely essential for life. Any liquid would allow this conjoining of molecules that can migrate through it. But water is particularly copacetic because of many of its characteristics. In particular, water is said to be a highly polar molecule. That is, the distribution of electrons orbiting around in the oxygen and two hydrogen atoms, looks a little bit like a Mickey Mouse hat with the big oxygen here and the two little hydrogens acting as ears, are not smoothly distributed. The positively charged nuclei are locked in place, but the electrons spend a lot more time orbiting around the oxygen than they do the hydrogen. Just this molecule on one side tends to be negatively charged on the oxygen side, and where the two ears are, since the electrons don't spend much time with the hydrogen atoms, it tends to be positively charged. Negatively charged down here, positively charged at the top. This means that molecules that are wandering through, which have a slight charge of their own, or perhaps even ions that have lost an electron and therefore are positively charged, will preferentially stick to the negatively charged part of the water molecule. When you put lots of water molecules together, you can then imagine them like a little scaffold on which more complex molecules can be built because of this essential polarity. abundant liquid water on the Earth clearly aided the development of life. Life's history is one of adaptation to changing conditions, some of which were brought about by the existence of life itself. The Earth was initially far too hot for molecules to survive. As it gradually cooled over the first 100 or 200 million years or so, the crust formed on the surface, and molecules rained down from many asteroids, not once every 100 million years or so like we have today, but perhaps every day raining down onto the surface. In addition, comets, which are sort of dirty snowballs, balls of ammonia and water ice, which contain within them the products out of which the solar system formed, including all these molecules we see in the net molecular clouds out of which stars form, are falling down out of this debris disk that surrounds the sun. Gradually, the Earth is sweeping it up, but all of this stuff is falling onto the surface. The sun was actually less bright than it is today, less luminous. It was putting out less energy. But the atmosphere of the Earth was very rich in carbon dioxide, even more than the amount of carbon dioxide we humans have put in it today from the numerous volcanoes that were constantly erupting on this still hot Earth. And that, as we'll see in the next lecture, provides a blanket which keeps the temperature warmer than it would otherwise be. And so the temperature was kept above the freezing point of water so that liquid water rained out of the original atmosphere. Within about 750 million years, life emerged. The oldest actual fossils we have of life are about 3.5 billion years old. That is only a billion years after the Earth formed. The first solid evidence we have for life is blue-green algae called cyanobacteria. They were the first to use photosynthesis and produce oxygen. The oxygen was poisonous to them, as a matter of fact, but it allowed the development of all the life that breathes oxygen that we have on Earth today. These blue-green algae collected into vast mats, living in symbiosis with bacteria and other primitive life that was around at the time. And we see their evidence today in geological formations called stromatolites, which are layered, intricately layered and folded regions of minerals that were collected by these mats of algae and layered in place as they died. All of these organisms, the bacteria and the cyanobacteria, were cells that had no nuclei. They lived over most of the 4 billion years of Earth's history, but now are found in only a few isolated places. They're also responsible for the geological deposits called banded iron formations. Iron, emerging from the interior of the Earth, where we learned most of it is initially soluble in water. But when it joins up with oxygen, it rusts, in other words, it precipitates out from the ocean. Banded deposits result from the periodic rise and fall of the oxygen levels in the water. Whether this was seasonal or some longer-term event, we don't know because we don't have a clock to measure 3.8 billion years ago. But these banded iron formations were laid down between the period 3.8 billion years ago and 1.8 billion years ago, and they form the principal iron ore deposits that we mine today. We've learned in discussing the history of agriculture that living things prefer carbon-12 over carbon-13. So rocks with a high carbon-12 to carbon-13 ratio provide evidence for early life. Such rocks with lifelike carbon ratios have been found on Aquilia Island off Greenland, for example. The rocks have been dated using the uranium-lead dating in zircons that we talked about last time. The zircons originally containing no lead provide an excellent clock with the double uranium-235 and uranium-238 decay chains to give us a check. There is some dispute about the exact date of the age of these Greenland rocks, the oldest ones found on Earth, but apparently it lies somewhere between 3.7 and 3.85 billion years, close enough as far as I'm concerned, implying that life was already prevalent only 700 million years after Earth formed. It then took another 3.8 billion years to get to us. It should be noted that we're here, but the sun has not yet lived even half its lifetime. We contain 50 trillion cells. If you average that out over time, it means we've been adding about 13,000 cells per year, but the rate has been far from uniform. For the first 2.5 billion years, there were not even cells with a nucleus. Multicellular organisms took another 500 million years to evolve. Subsequent evolution produced an elaborate feedback loop between the changes in life and the changes that life effected on Earth's atmosphere, as we'll discuss next time. Life emerged on Earth from commonplace interstellar chemicals after less than 10% of our sun's lifetime was complete. For billions of years, it was dominated by the physical conditions in which it found itself. Then life gradually took over the planet. In the next lecture, we'll see how life also took over the atmosphere.